I apologize for technical problems that led to having lost half of my lecture, which I'm re-recording now, and just patching the two halves of the lectures. Unfortunately, the software I'm using is not quite performing as I hoped. We were saying, defining what is called the kinetic distances between two configurations. And we were saying, well, we would like this distance to measure the proximity in terms of diffusion of two configurations. And we came across with this idea of taking two configurations and then let them evolve in a timescale tau to some configuration y. And then looking at the integral over the final position. And now the idea was that if x1 and x2 are in the same basin, and if tau is chosen to be of the size of the thermalization timescales in local basin, then within the timescale tau, both these distributions will basically, so this is, you can think about x1 as a delta function in x1 and x2, and after the time tau, from this, let me distinguish between the two configurations. So x1, let me draw it in blue, and x2, let me draw it in black. Then from x1, I wait time tau, and after a time tau, x1 has become locally a Boltzmann distribution. Similarly, from x time 2, I run many simulations, and after a time tau, from the point x2, I converge to the same distribution, because the time tau is sufficient to achieve local thermalization. Well, clearly, when I take the difference, this will be basically 0 up to statistical noise in sampling these distributions. So this will be, in general, strictly speaking, 0. Exactly speaking, it will be a small number in practice. Conversely, if I choose on the same energy landscape x1 to be on one side of the basin and x2 to be on the other side of the basin, and I wait time tau, this will converge to this and this will converge to this. And the difference between the two will remain finite. So that's a very natural thing to be doing if I want to define a kinetic distance. Now it turns out that you can write this combination in a form that makes explicit the definition of collective variable, which is appropriate to describe the long-time dynamics. Why? Because if I perform a spectral representation of this guy, then let me write it this way. Sum over n, right n, y, left n, x1 e to the negative lambda n tau, negative sum over m are my, l m, x2 e to the negative xn 2. And of course, this is not very readable here. So let me move my face somewhere else. Maybe here, Professor. Well, you don't need my face for the time being. You'll see my face in a moment. Now, typically, there's this weighted sum here. What I would like to do is to, at least in this discussion, when I'm interested in coordinates, get rid of the exponent. You can work with it and take and drag them along with you. It doesn't matter. But I want to work in an idea case, just for the sake of the present discussion, which I have a nice gap, and I'm choosing tau in the middle of the gap. And this gap is such that if I do that, all the all the terms, exponential terms above the gap will be exponentially suppressed, so that will be 0. But all the terms below the gap will be so small that I can approximate them with 1. Now, if you can do that, let me move this thing here a little bit above the gap, below the gap. Now, if you can do that, then you simply, the result of doing this is simply that of restricting the sum to a maximum n, here to a finite number of terms, and getting rid of this. Okay, now we can still do better. How? Well, the idea is then to multiply, to sort of complete the square, sorry, to expand the square and do the integral over dy. And this is a part that can be done, and I will probably do that explicitly in another lecture. In this lecture, for sake of putting all the logical terms in a single lecture, I will skip this derivation. And the result of this is that after you do this, the kinetic distance will stop depending on tau, because tau, as long as tau is in the gap, all the exponential terms vanish. And it turns out that becomes essentially the Euclidean distance measured on n coordinates, which are just the left eigenmodes of the Fokker-Planck operator. So maybe it's time to restore my ugly face somewhere here. There we go. So the y dependency has dropped out because of normalization, essentially. And then you use some orthogonality conditions between the different eigenstates of your Fokker-Planck operator. And you arrive to an expression like this. Now, what this is telling me is that there is an ideal mapping from 3n coordinates, x, to only, well, this n max, let's call it n max, the number of eigenvalues below the gap. So that's a much smaller number. That's the number of eigenstates below the gap. And the mapping is between the point x and the function Ln of x. And there are n max of them. So it's a dimensional reduction from 3n to n max. And this dimensional reduction is built in such a way that is most likely faithful of the underlying dynamics, because it gets that this new Euclidean distance in this flat manifold, Euclidean manifold, is actually representative of the kinetic distance in the original configuration space, at least up to exponentially small corrections. So if you think about this, now if you're a mathematician, a mathematics lover, like sometimes I am, you would like to speculate on connections, and it looks a little bit like when you locally transform away gravity in general relativity, and you discover you can transform away gravity and get a locally Minkowskian manifold, but you need a non-trivial coordinate transformation to do that. Now we are in a similar situation here. We have a configuration space. The kinetic distance in this configuration space is a highly non-trivial function of the coordinates, highly non-linear, whatever. But you can transform all this complicacy away by defining this set of very powerful reaction, let's say collective variables. And in this new manifold, after you're doing this coordinate transformation, The kinetic information is trivial. In the new manifold has a Euclidean geometry. The distance is just Euclidean distance. You're transformed away the kinetics. There's some kind of a highly non-trivial and highly deep connections, if you want. And that, in principle, there are so many connections with geometry of in configuration space. You can actually map away diffusion into you can map away, in some sense, all the physics of stochastic diffusions into a redefinition of metrics and geometry of your configuration space. But that's more for those who sort of get kind of a twist of emotion by seeing mathematics in action, and not particularly deep, by the way, in this case. Okay, this is all. So at least we have an idea of what we would like to have as an ideal collective variable for featurizing and performing dimensional reduction. But I think you all appreciate this is completely useless from a practical point of view, because if I were hoping to solve for the Ln states, then I basically would be able to diagonalize the Fokker-Planck operator. If I can diagonalize the Fokker-Planck operator, if I have the left eigenstates, I would have the right eigenstates. They're just related by a non-unitary Boltzmann factor. And if I have the right hand side, I just recombine the probabilities and have all the information I need. Why bother in doing all this? And the whole point of complex systems is that you can never really diagonalize the Fokker-Planck operator for, say, 3,000 variables. So what do you do in practice? Well, in practice, featurization is unavoidably phenomenological. So you build up, based on physical-chemical intuition, you try to identify collective variables which you hope correlate with the kinetic distance. And I give an example of how you do that in some specific case. And I take the case of a polypeptide chain, typically a polymer. And you might have side chains. And this might be, oh sorry, it still hasn't showed up, still hasn't refreshed the screen. Waiting for the screen to refresh. Come on. My screen doesn't see, oh, okay, it has refreshed. So you have a collection, maybe you have a polymer, and this polymer is made by a collection of atoms. And suppose that this geometrical topology sort of structure of my chain is, as it usually is, dictated by covalent bonds. Now, as you can imagine, covalent bonds are chemistry. They are very hard. They are not thermally broken. They are hundreds or thousands of kT, so they're very stable. As a result of which, for instance, if you want to move this atom somewhere, leaving all the others where they are, for instance, if you would pull this atom in this direction, then it would amount to narrowing this angle, right? And stretching these bonds. Clearly, this upsets the covalent binding energy a lot. And that corresponds to a very high frequency in an effective harmonic oscillator, which means that this motion, vibrations, or along the distance of the covalent bonds, or angular vibrations, are very fast. So if I'm interested in a kinetic distance at the time scale tau that is much lower than the typical period of these angular or bound stretching vibrations, I really don't care about them. On the other hand, so I don't really need all 3 n coordinates here for defining my kinetic distance at that time scale. On the other hand, if you think about, there are many movements which do not alter any topology of the chain. For instance, think about rotating this part of the polymer around this axis. Or rotate this side chain, or maybe it's, I don't know, an aromatic ring, around this axis. Now clearly you can do that without upsetting calling points. And in fact, typically, there's several orders of magnitude between the typical oscillation of these movements and the typical oscillation of bone stretching or angular bending. These are called dihedral angle. And if you take Gianluca Lattanzi's course on computational biophysics and Luca Tubiana course on computational biophysics for the QCB degree, or you borrow it if you're a physics degree, check if you can, I don't know. Then you discover the definition. Basically, a dihedral angle is an angle you form between this plane and, in this case, this plane. So it's an angle between planes. And you need 4 points to define an angle between planes because you need 3 points to define a plane. I don't want to go into these details. All I'm saying is that it is clear that a set of dihedral angles is likely to describe fairly well the slow dynamics. And if you have two different diagonal angle configurations in dihedral angle, then they are really distant because they have to diffuse together. If you have two configurations in which maybe some slight detail in the atomic composition is changed, but the dihedral angle are the same, then basically within a very short time scales they diffuse on the same Boltzmann distribution. So for instance, typically people think dihedral angle for disordered polymers are decent choices of features, while we think they correlate decently with the kinetic distance. Well, guys, this is research. As you move very close to the research field, then you lose uniqueness of your choice, and you leave the territory where the best option is always there, and you know exactly what to be doing. For instance, if you work in particle physics, well, then you know that if you want to do certain calculations, you better use covariant gauge fixing, and if you want to do other calculations, then you want to do a unitary gauge transformations. People have worked that out completely. And then your research would be on the application on the scheme on the new system rather than on the developing of theory for that. When you reach the frontier of research, then things get muddy. But that's where the action is actually, in every field, and not only in this field. Okay, so suppose we have achieved the featurization. As soon as my window will refresh, I'll continue. Come on, wake up. Well, as it doesn't do it, I keep on writing and I say, now let's do that. Let's consider dimensional reduction or clustering. The second step is actually clustering. Which often goes through a step called dimensional reduction. Okay, so featurization is a form of dimensional reduction, which is phenomenological. Some approach to identify the Markov states go through a next step, which is a dimensional reduction, which is really based on trying to use the information on the features to compute the Ln's functions. And in the literature, you find methods such as TICA, time-independent component analysis. These are ways of using the available stochastic informations after featurization to perform an inference, a statistically best inference of what the Ln should look like in the space of features. Or better, in the space of data you've generated. And I don't want to go too much into that. It's technical, it's research, it's probably too much information for the average student of this course. What I think of doing is maybe at the end of the course select a couple of topic arguments that are in the notes or in the literature, and maybe the students can, as a last chapter of the course, go deeper into one of these subjects depending on their own interest. So I will not go into that. And after you've done that, then you have a set of points in some space of maybe collective variables, and you want to cluster them. And then you use typical algorithms that try to base the clustering on a proximity in the space you've defined. And it's interesting because very often you're misled in this clustering. So basically clustering takes a bunch of data with clouds and makes a decision and says, okay, these points belong to the same group, this point belongs to the same group, and this point belongs to the same group, and now I can call this Markov state I, J, and K. And all I want to do here is to point out that when you do this, you might very easily run into troubles. For instance, consider the following situation. You have all these points densely packed right here, and you have another set of points. Maybe I'll do it like this. Like this. And maybe here I put a little bit of space. Now I think we would all agree that this form a state and this form a state. However, if you don't have exactly a kinetic distance that is perfect, but you use a proxy of the kinetic distance, you might run into errors, and your distance might decide that this point is closer to this point than it actually is to this point. And maybe they will assign this to this. So any error on the kinetic distance proxy you're using will determine a potentially uncontrolled error in the way you find microstates. And so there are sophisticated algorithms, for instance, one introduced by an Italian scientist, Francisco Laio, with whom we collaborate, and for those who participate to the double program with CISA could take his lectures on data science. He has invented a very smart algorithm in which he follows the density of points stochastically estimated and is able very much to distinguish between these situations, and he published it on Science. For the purpose of this talk, all I want to say is that, and I want to wrap up the concept, is that in order to find a Markov state, you have to go through a very careful theoretical scheme. It's basically a field in itself, and it's a field for data science on the one hand and statistical computing on the other hand. And basically there are two main challenges. Challenge number one, how to perform a meaningful dimensional reduction that takes into account of kinetics, and challenge number two, how to cluster together configuration if assuming that your definition of metric does not really correspond to the kinetic distance, because it will never actually do. And that's where data science and statistics come together into a big data problem which is specific for molecular simulation or for complex system simulations in general. In the notes you'll find some details about these methods. I don't ask you now to remember them, just for you to keep in mind that, having written down the Markov states doesn't simply correspond to be able to, all in a nutshell, generate them. But after you have a definition of Markov states, well, now you need, suppose I've found this Markov states with all my clouds. I've assigned this point to the states. Now I need come on, my connection today is very slow. I'm waiting for. But once you have your Markov state and you have assigned them to different states, you still need the density, the kinetic metrics. And how do you work them out? Well, first of all, you can take the same data that you use to find the microstates. They are trajectories, after all. And then you can use them to count how many times you move from one to the other and get a stochastic estimate. Very often, the stochastic estimate will have a low statistics, so you might have large errors. So what you want to do is you want to reinitiate more configurations, more simulations. You pick up another point from here, and you run some simulation, and you count how many times you end up in the other one. And you do it many, many times. So by doing this, you repeat, you repeat, you repeat, you repeat, and eventually fill up with the accuracy you want your kinetic metrics. And once you have your kinetic metrics, then basically you're done. You can use it to step ahead and write your dynamics in terms of a microstate model. The last thing I want to say is that it might seem that this is a hopeless operation, and actually that it's even not beneficial to go through the microstate model formalism if you have to do all this additional work, finding the microstate, computing the rate. Is it really worth it? What is the big gain of going to the microstate description? I'm losing resolution and I have a lot of non-trivial work and additional simulations. It might look to some like a waste of time. And I want to emphasize why this is not a waste of time at all. There are essentially two main reasons. The first reason is we understand things much better because our brain is used to think two-dimensionally and not, or one-dimensionally, not multidimensionally. And after you have done the reduction to a microstate, all of a sudden you might have a way to visualize how a process works. Let me give an example. Let me draw a set of state. And suppose I'm interested in what is called a reactive process. What is a reactive process? I want to understand what is the most likely way to go from state R, which I call the reactant, to state P, that is called the product. We'll focus on this problem in the next set of lectures very carefully. But I already want to anticipate that to show you how things can become easy once you define microstate. Now, in 3 dimensions, that's you have a bunch of configurations and another bunch of configuration. You want to know how you go from there to there in configuration space. Sorry, not 3 dimensions, 3n dimensions, and that's a very multidimensional space. And you generate many trajectories, and maybe you see several events that do that. But then you look at all these trajectories, and they look all different because you never see the same trajectory twice in your life. It's a stochastic property, and the probability density of a single trajectory connecting R to P. The measure of this is 0. I mean, the statistical weight of a single event is like the integral of a point, right? So you never see twice the same trajectory. So you can never understand any mechanism. However, suppose you now do your microstate model, and then you have rates connecting all the states, and maybe you discover that now I'm going to draw in red that there are. Let me draw in red, and let me use a thickness to represent the size of the kinetic matrix elements. So suppose these are very large rates, and maybe these are relatively smaller rates, and everything else is very light. Then if this is the case, then you, even without having any knowledge of stochastic descriptors of the active process, you would imagine that this process can proceed mostly through two main reactive channels. This channel, sorry, let me use the same color, channel 1 and channel 2. You have to be more quantitative, of course, but what I want to say is that by going to the microstate model, we mapped a crazy multidimensional channel in a form that we can even draw on a piece of paper and get insight by looking at that. In some senses, it's very similar to what Feynman achieved by relating a quantum field theory process, which is an infinite dimensional problem, into a diagram. Once you can draw it as a diagram, it immediately makes sense what is happening, what's going on. And you can classify diagrams, you can think of leading diagrams, sub-leading diagrams, and all that. So that synthesization of a huge amount of process, of information into a few concepts, a few processes, a few representative elements was key to understanding quantum field theory. Similar in this case, condensing all the information configuration space into a microstate model allows us to sort of visualize what's going on in the system. So, number one reason for going to microstate is really physics insight into complex system multidimensional space. And the second reason is numerical efficiency. Suppose we are now working with highly multidimensional space. And suppose our space is full of energy barriers everywhere. It takes a huge time to become ergodic. Now you want to start dynamics on this space. What you can do is to integrate forward the equations of motion. So you start from your initial point and you shoot a long trajectory. And you shoot, and you shoot. And now I could draw forever because the time it takes to go over configuration space and maybe to reach once a point that sits here, if there is a barrier in here, is exponentially long, right? That's a rare event. And maybe it's an exponentially large number of rare events. It's not going to work. And that's why until 2010, nobody could have ever used molecular dynamics simulation to fold a protein, for instance. And in 2010, they could do that for extremely fast folding proteins. There are pieces of proteins that have been engineered to fold on super fast time scales, so to have a simpler kinetics. And they can only do that by building a supercomputer that has all the molecular dynamics algorithm implemented in hardware, not as a software. So you have about 2,000 factor speed up with respect to standard supercomputers. And they're running full time for a third of a year or so. Now, you see, this is highly inefficient. However, Mr. Vijay Pandey at the University of Stanford, now not anymore, he's become a venture capitalist, living research forever. I wonder how much they paid him to do that. Well, he came out with this brilliant idea, says, we don't have a supercomputer that can solve a complex problem like this, but we have millions of ordinary computers distributed around the planet that are on idle more than 50% of their time. Think about not only your computer, but the computer of all the offices in the world, clerical jobs, banks, administrative computers, desktops. The most of the time, they are on idle. So if people volunteer, they can sign up to a program called Folding at Home. You can Google it and you'll find a wealth of information. And what what your computer will do, when you put it on idle, you will go to the server of the Folding at Home server. Will pick up a little bit of initial condition from a point and run a short molecular dynamics trajectory. Very short because it's a small computer. And after it is done, maybe a nanosecond, it will send it back. Now, the server will take care of doing the following. He has many states, for instance, perhaps an initial guess of the states, and then he distributes the initial condition to the millions of computers in different states, and maybe in 1 nanosecond, maybe there's 10,000 of these states, so they're very close to one another, right? And in 1 nanosecond, you can see some transitions. Now, individually, each computer will crunch numbers for a few hours and maybe get just a nanoseconds of dynamics. But the millions of computers simultaneously, we get a huge amount of statistic done. Now, if you were to use them to integrate a single trajectory, you would have to call them in series, and that would not give you any speed up. But using the Markov state model formalism, if you want to recombine all this information stochastically through a Markov state model equation, then you can distribute this and do it in parallel in a millionfold faster way. And that's what it is done, and that's how they could come across solving solutions to unsolvable problems by exploiting statistical mechanics and globalization together. I think this is a very exciting idea. I think you have to give credit to the guy here to be able to come up with such a brilliant way of interpreting how science should work in the globalization time. I think it explains to you why people are interested in Markov state models also as a way of speeding up calculations. Okay, I think I've exhausted more or less what I wanted to tell you about Markov state models. I would like you to stick to the material that is on the notes, and I've written relatively fewer formulas in these lectures. But then we'll start crunching more formulas starting in the next lecture. Bye-bye.